people at home. So we just went out in the hall and we rolled a tennis ball, just like this, down the hall, okay? And then we tried to make a motion diagram, a particle diagram out of it. Well, the thing is, the diagram is just showing a straight line, but in reality, there was a ramp, okay? In reality, we rolled the ball down a ramp, okay? And the ball came down a straight ramp, and it hit the floor, then it rolled across the floor until it stopped. And this is our diagram of it. So you see the dots here getting further and further apart. That's showing acceleration, okay? And if we drew a vector on here for velocity, the vector would be getting longer and longer and longer. That'd be nice vectors for qualitative velocity, right? Qualitative means we're just showing the quality of it. We're not actually giving it a quantitative number. So we rolled it down this ramp. And notice after the ramp, our velocity vectors are exactly the same for a little while. And then they start getting smaller and smaller because they have friction against the floor, and the ball eventually stops, okay? Now, I would ask you at home to think about this. We still have the ramp, okay? And this is where our ball got to the end of the ramp. But if you just looked at this line, what would that tell you about the ramp? How there's a lot more dots here. And the ball also didn't go as far. You can notice that. The ball didn't go as far. Well, what that would tell you about the ramp at home is that this ramp was set on the floor, but it wasn't nearly as steep, okay? So that's our little quick lesson on using a particle diagram and rolling a tennis ball down the hall. It's all very, very simple, okay? It's all very, very simple. Well, the next thing we're going to do is we're going to go out in the hall, we're going to do a little lab, and we're going to learn how to calculate the velocity of a car. And in this situation, we're going to use a remote control car. So with the remote control car, we're going to go in the hall, we're going to calculate its velocity. Now, normally we use the metric system, so we calculate velocity in meters per second or kilometers per hour if it's a big car. But since we're in the hall, and there are very clearly defined tiles on the floor, we're going to calculate the velocity of our car in tiles per second, right? Instead of meters per second, we'll do tiles per second. Does that make sense to everyone? So we're going to learn how to calculate velocity. We're going to do it, and then we're going to graph it, okay? We're going to graph it qualitatively and then quantitatively. We're going to actually put numbers on our graph, okay? So let's take a look first at the velocity formula. If you look on the speedometer of your car, and here in the United States, and just about nowhere else, how do we calculate the velocity of our car? If you're going 55, you're going 55 what? Miles per hour, that's exactly right. So if we looked at 55 miles per hour, what that really means is 55 miles per hour is equal to your velocity. Now, 55 miles, that is a unit of what? Distance. And hour is a unit of what? Time. And this is velocity. Your velocity is 55 miles per hour. That little p there is the division sign. Make sense? Okay. Logically, by looking at this, can you tell me what the formula for velocity is? And I haven't even given you your physics tables. Can anyone, by looking at this simple formula, tell me the formula for velocity that will show up in the physics table? Okay, for the sake of time, go.
XD over T, or D over T?
V is equal to D over T. That is the formula for velocity. And you've known that your whole life by seeing your parents drive their car at 55 miles per hour. Miles per hour. Does that make sense? Right, let's go out in the hall. Let's do some calculating. What we're going to need to calculate. We can already measure the distance in tiles on the floor, right? So what else are we going to have to measure? Time. So what are you going to use to measure the time? Your cell phone with a stopwatch on it. That's right. And people at home, you can watch the video and you can also time it with your cell phone. All right? All right, let's do it. Fancy editing time. All right, ladies and gentlemen. First, I've got the car way back here. All right? And the reason is I'm going to let it get a run and go. So we're already up to our maximum speed, okay? When we cross this line right here, the line from red to gray, that's our start line, okay? And we're going to drive to the next line there, way down there, where it changes from red to gray again, okay? So first thing we're going to need to do, velocity. Oh, I'm not going to put you on the video. Just got your feet, okay? It's like one of those news videos. Anyway, first we have to do in velocity, the velocity formula, velocity is equal to distance over time. I can't make a T because I'm holding the phone. All right. Velocity is equal to distance over time. So we need to calculate this distance. So let's do that. Let's count our tiles here. Ready? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 tiles. 26 tiles. Now, people at home, you can participate in this anarchy. You're going to need to get your own stopwatch out, okay? We're going to drive this car. When it crosses this line right here, you start it. When it crosses this line right here, you stop it. Does that make sense? Okay. I'm going to need somebody that can drive this car. Who is capable of driving a remote control car? People at home, here we go. And I'm going to tell you, don't start yet. All right, go. Hold it wide open. Here we go again. Ready? Go. Wait at home. Hold it wide open. Hold it wide open, girl. And follow it. All right, stop. I apologize, people at home. I can't edit out my errors, okay? She's going to hit go. When I say go to her, she's going to go. And then don't forget, you're going to start your stopwatch when we go across right here. Ready? Go. Now. People at home, sorry, we had a crash in the last one. It's okay, here we go. He's going to start it, hold it wide open. And boom. Good job. All right, so we're going to calculate the velocity of that car, okay? And here's what we did. Hopefully you people at home timed it. All right? What we got here, we got two measurements. One person had 5 seconds exactly, and the other person had 4.97 seconds. So we're going to go with 5 seconds. So we're going to solve this formula. Velocity is equal to distance over time. Okay? So the velocity of Big Blue, our remote control car, what was the distance? Anybody remember?
26 tiles.
Yeah, the distance was 26 tiles. And the time it took was?
5 seconds.
5 seconds. So you can calculate the velocity of this car. And it is going to be 5.2 tiles per second, or 5.2 TPS, we could even call it. Does that make sense? Am I making a math mistake? Is 26 divided by 5, isn't that 5.2? Okay, so there we go. 5.2 tiles per second. That's the velocity of that car. Now, here's what we can very easily do. We're going to make a particle diagram, which means we're just going to use a dot to represent the car. Okay? So, boom. Here is our start line. And we're going to make lines to represent every tile. So check this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's double these up. 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 26 tiles. All right. So there's 26 dashes on here. All right. Now, I want you to imagine there is a camera. This is an old-fashioned camera, okay? I don't know. Here, there's the flash on it. A really old-fashioned camera. And this old-fashioned camera, let's fix the lens a little bit. There, it looks a little bit better. Now, this old-fashioned camera takes a picture one every second. So it takes a picture every second. So it's going to take 5 pictures. Does that make sense? So right now, I want you to put a dot on here in the right place. Now remember, there's no acceleration because our car was already up to speed by the time it crossed the start line, right? Does that make sense to everybody? So you're going to put 5 dots on this graph and label exactly what distance the car has gone after each second. Does that make sense to you? All right, go. People at home, you try this. All right, people at home, I'm going to pretend that you actually did this. I'm going to pretend that you did your work. You're going to be turning it in, so I hope you did. All right. Here is our line. Watch how easily I can do this. I can put these dots on here, or I could just put one dot. What if I wanted to just put the dot on where this car would be after 3 seconds? I can use this formula. Velocity is equal to distance over time. The velocity, the V, is 5.2 tiles per second. How far would it have gone after 3 seconds? See how simply I could do that? V is equal to D over T. So I can just say 3 times 5.2. It's gone 15.6 tiles. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.6, you should have a dot at 3 seconds that's at 15.6 tiles. Do y'all have a dot there? That makes sense? Is your third dot at 15.6 tiles? Exactly. Does this make sense to everybody? Your first dot will be at 5.2 tiles. 1, 2, 3, 4, 5.2 tiles. Your second dot will be at 10.4 tiles. 6, 7, 8, 9, 10.4. And then we would notice that the dots are always going to be the same distance. Because what do we know about this car? It's traveling at a constant velocity. So the last thing I want to show you is when we're really talking about this V, we can put a little bar over it. And that means the velocity is constant. It's locked in. The car is traveling the exact same speed or velocity the entire time. Now I'm going to switch this graph up just a little bit. I'm going to switch this graph up just a little bit for you people here in class and you people at home. The velocity of this car was 5.2 tiles per second. Now what if I made a graph that looked like this? Okay. Now this is 0, and what's going by right here is time. Okay? So this is a line graph, but we're also showing the negative y. Does that make sense? And this is time going by, time. If I was going to graph this, fill out this graph for that car, I would go like this. 1, 2, 3, 4, 5, 6. At 5.2, I could start an arrow, and this would represent what the car was doing the whole time. What do you think about that? This is a graph, velocity. We've got positive and negative, right? Positive is up, negative is down. If we label this 1, 2, 3, 4, 5, boom, 5.2, this velocity occurs over all the time that went by. Does that make sense? All right, now that you know this, now that we've seen this little one, we're going to go out and we are going to graph this car doing something different. All right? And that'll be the last thing we do. We're going to graph this car doing something different. All right, now we're back in the hall. There's our door, so you're oriented. There's the door. So right here, this was our start line, okay? And then down the hall, down there, there is our finish line. Keep that in mind. Keep in mind where the start line and the finish line is. All right, now we're going to do a new graph. All right, everybody. Notice that I'm standing at the finish line. I'm standing at the finish line, and the starting line is down there. So Katie's going to film this. I'm going to get my speed up before I cross the finish line. All right, Cynthia, filming now. So think about what type of velocity are we looking at? If I'm standing on the starting line now, and the car came towards me, back towards me, what type of velocity would that mean from my perspective? From my perspective, what is the velocity of the car? So we know that this car has a velocity of 5.2 tiles per second when it's in motion. And if we're looking at a graph like this with velocity, right? And let's say 1, 2, 3, 4, 5, 6. If we're looking at, excuse me. If we're looking at this graph, this is what the car was doing for the first exercise. So what would the car be doing from the last thing we just filmed? What do you think? How would I perceive that velocity if I was standing on the starting line and the car's coming back towards me?
The same thing, just in the fourth quadrant. So the negative 5.2.
Exactly. This is what she meant by the fourth quadrant, people at home. But the car is now coming towards me, so its velocity is negative. It's not going away from the starting line. It's coming towards the starting line. So if we're going to graph the velocity of the car, the first trial, there it is. The second trial, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.2. Well, I'm just going to try to make it the same. This is what we just, well, these are supposed to be the same, obviously. But if we're showing a negative velocity, we'll put the line down here. Does that make sense to everybody? Okay, I'm going to give you a worksheet that has some of these thoughts in it, and then you'll have to try to work it on your own.